Bismillah ar-Rahman ar-Rahim. Today we will continue our session of first order logic, the predicate logic. Today we will discuss that how we interact with using FOL, first order logic, in knowledge bases. We have discussed the problem of Wumpus world in chapter number 7, which is there in your book as well. So let's assume that we are talking about the Wumpus world agent, which we have already discussed in the class, and perceives a smell and a breeze, but no glitter at the given time. Let's suppose t is equal to 5. So how we will inform the knowledge base, because there is always a tell and ask relationship whenever we talk about the informing the knowledge base and whenever we want to make a query with the knowledge base. So in the given model, the tell will inform the knowledge base that the KB, and you can see in the parameters as well. And what is the percept? That there is a smell and a breeze as well. So smell, comma breeze, but no glitter. So no glitter is there at the given time t is equal to 5. So now it is up to the knowledge base to respond to this particular query, and of course the agent has to take an appropriate action based on the logical formulation. So what we want to ask from the knowledge base, that the KB, that there exists A. It means an action A is there, which is an appropriate action at given point 5. So that is ask KB, there exists a action A comma 5. So the question is that does that KB entail any particular action at t is equal to 5? That is important. Is there any action which a KB can take at that particular time? So let's assume for a moment that the best action here is to shoot, because there is no other action, or all the navigation or the other possibilities have been explored. So the answer will be that the given point in time, the best action A is the shoot. And obviously that it means that A, which is a variable, is replaced by shoot. That is called a substitution, which is available from the binding list. Because what actions are possible? Either the agent can move upward, either can agent move downwards, left or right, or agent has to shoot. So here the best substitution will be shoot. So given a sentence S and a substitution sigma, so S sigma denote the result plugging sigma into S. So whatever the situation is, if you want to generalize it for any given sentence, the substitution is represented by sigma. So here in that case, if you want to see that S is equal to smarter x comma y, so it means that you have to come up with a sigma, which is the replacement of x, or you can say the instantiation of x and the instantiation of y. So let's suppose the x is Hillary and y is Bill. So S sigma will be the smarter Hillary comma Bill, as we did in the above example where we have represented this A oblique shoot. So that is the best representation. So ask KBS, return some oblique all sigma. So all possibilities or the few possibilities if they are there, such that the KB entails as sigma. So that action must be entailed in that particular knowledge base. So if that action is not entailed, obviously that action cannot be taken. So that we have already discussed in the entailment section and the inference section, and you can refer to the previous slide. So knowledge base for the Wumpus world. Now we talk about the concept of reflex action. So whenever we talk about a reflex action, it means that there is nothing to think about, because the appropriate conditions are there and we know exactly what best action suits for it. For example, for all b comma g comma t, how we represent it? For all, it is true for it is a universal truth. So therefore, for all B represents the breeze, and let's suppose G represents the gold, and T is the given T. So the percept is that, let's suppose if we have a smell, comma B, comma G at a given time T, so it implies that we have smelt at given point in T. Similarly, if we are at gold, that is why in the next tense sentence you can see a glitter. So it means we are at gold T. So that is some kind of an inference we can make out of those sentences. So if there is a smell at a given point in time, so it means we have smelt at given point in time. If we have a glitter at a given point in time, it means we are at gold at given point in time. So the reflex statement or a reflex action is represented as for all t at gold t. So now what to do? Now let's suppose we have a glitter. We are at gold. So what to do? So if you talk about rational action, so what an agent should do? So if the agent is at gold, so the action is to grab the gold, because that is the task which is being assigned to it. So let's suppose if agent reaches out to a particular state where the gold is, so the appropriate action will be to grab it. So that is represented as a reflex action, and you can see that it represents a statement that for all t at gold t implies action grab comma t. So this is an FOL statement where t is the variable, at gold is what is a predicate, and what is the action? Action itself is a predicate, and grab comma t is to be invoked. So reflex with internal state. Do we have the gold already? Now, one question which comes to our mind is that we are at gold, but we are not holding the gold. Now let's suppose if I want to represent this internal condition as well. So if I want to represent this condition, then I will say for all t at gold t, and I'm not holding the t. So that differentiate the two conditions. One is that you are at gold and you are holding it, so that's fine. So if you are not holding it, then the action will be the grab t. So that is why it is represented as for all t at gold t, and not holding gold t implies action grab comma t. So holding gold comma t cannot be observed, implies keeping track of change is also essential. So in whatever the knowledge base you are looking for, it is also very important to know what are the internal conditions, and you have to invoke those internal conditions, or you want to represent those internal conditions in terms of your statements, so that it can be clearly represented. Deducing hidden properties, that is another important aspect while we are representing our knowledge base in the form of first order logic or a predicate form of logic. So before explaining you what is meant by the hidden properties, I first want to introduce you the concept of diagnostic rules versus the causal rules. So, whenever we say the diagnostic rule, it means that we infer cause from the effect. For example, let's suppose if you are representing in your knowledge base that how a doctor diagnose a certain, let's suppose, illness or disease in a patient. So what he normally does, he asked various questions to you and to find out what causes you have. Maybe you have the nausea, maybe you are having body pain, maybe you are having throat pain or infection, or maybe you are having fever. So what are these? These are all causes. So, as you know, that in a disease you might have similar causes. So because the doctor is a specialized person who has a knowledge of his subject or a domain, so what they do, they try to find out all those causes. They physically see you in the clinic as well, and if they have certain doubts, they might ask you to go for a particular test to verify it. But all these things leads to the final conclusion, or you can say the diagnosis. So it is a diagnostic procedure where what you do, you see the causes and you try to find out the effect so that you can remove those effects, and that is called diagnostic. Let's take another example. Let's see, we take our car to the mechanic and we just tell them that this is happening in my car. So the mechanic is, a person who has that domain knowledge. So what he does, he look into the car, into the engine, and try to find out what is the cause of this. Let's suppose I have a problem that my car is heating up. So it's a cause. So there may be certain causes which can be which can be which are there. So we have to identify all those effects. What are the effects? The effect may be the car is heating up. The effect may be the engine is not taking the full power. The effect may be there is a starting problem. The effect may be that there is a wobbling. So what are these? These are various effects. Now the task of the mechanic is to determine what is the actual cause of those effects. Similarly, I gave you the example of a medical doctor. So what they do, they try to infer those effects, infer those causes. And what you do, you let them know what are the effects in terms of fever, in terms of pain, in terms of headache. What are these? These are effects. So what they try to find out the exact diagnosis, the cause of those effects, so that that cause can be identified and then can be rectified. Similarly, we might have causal rules as well. So causal rule works it's a totally reverse of diagnostic rules procedure. There, the it is already established that what is the problem, the cause is known to us. Then but there is a need to verify it, there is need to confirm it. So what we do is we try to confirm those effects, whether those effects are there or not. Let's suppose you go to a doctor and the doctor exactly knows by looking to you and talking to you that you have a dengue fever, but they cannot make a statement. So what they try to do, they want to know whether you have those effects or not. If you have those effects, or they think they need to verify it from the lab procedures or the laboratory experiments, then they will ask you to go for a specific test which confirms the cause. So there are two ways in which we can proceed. Either we can infer cause from effect, or we infer effect from cause. So one is called the diagnostic procedure, the second is called the causal procedure. So normally in normal circumstances, mostly we go for the diagnostic procedures because mostly we have various effects and we'll try to find out the cause. But once the model is clearly defined, and once you have that domain knowledge, and once you have that experience, you might go for the causal tree as well. And so these are the two possibilities you have. Now let's see on the top that we talk about the hidden properties. It means something which is not apparent in the statement. But we try to take out that information from the given statement. Let's suppose if you see the top statement, it says that for all x comma t, add agent x comma t. Let's suppose it means that for all x comma t, add agent comma x comma t, it means agent is that particular location at a given time t, and they fell or he felt the smell at the given time in t. It means that cell is smelly or that location is smelly. That is the implication. And in the next statement you can see, for all x comma t at agent x comma t and breeze, there is a breeze. So breeze is what? Is in effect, this implies that that particular location is breezy. So it means that is something which is not there, but you drive that information out of it, which can be used for your own decisions. So neither of these is complete. Example, the causal rules doesn't say whether squares far away from pits can be breezy. No, that is not there. दोनों में नहीं है. That is only defines the situation. So how you define the breezy predicate? Let's suppose you want to explain the breezy predicate. For all y, breezy y. So which cells will be breezy? This will be true for all those cells in the Wumpus world, that those are breezy. Uh, so there exists pit in the x, and that x is adjacent to the y. That is the condition. Remember, we have that condition that if a cell is breezy, it means in the adjacent squares there might have pits. So one cell is the cell which is breezy, and the other cell is the cell which is adjacent to that breezy cell. So one is represented as x, one is represented as y. So for all y, अब हम breezy की we are giving the statement for the breezy. So for all y, breezy y, it means that y is breezy. When it will be breezy? Whenever there exists x, there may be a pit at x which is and that x must be adjacent to the y. That is why it is represented with conjunction with the pit x predicate. So that is why the statement will be there exists x, pit x, and adjust x comma y. Keeping track of change. So whenever we talk about such systems or such problems, there is always a change. Why there is a change? Because the states have been changing. While when an agent makes a first move, let's suppose from 1 1 to 1 2, the state is changed. Now let's assume the agent makes a move from 1 2 to 2 2, again the state is changed. So, whenever we are representing such situations, there is always a change in the states, and we have to keep track of that change. Okay, so that is represented in terms of situations as well. So facts hold in situations. Let's assume when I am playing, let's suppose a tic-tac-toe, and I make the first move, and you make the second. Now the situation is changed. Now I will make the next move. When I will make the next move, you will reply it. Then I will make the next move. So every time the situation is changing. Maybe I am looking for the center square for the first time. Maybe I'm looking for the corner square for the next time, so on and so forth. Let's suppose if you are talking about driving, again, the situation is changing all the time. You drive, when you move on, you have a new situation. Similarly, in the Wumpus world problem, whenever the agent moves to the next cell, there is a new situation, there is a new state. And that is why every situation is represented with respect to time, as you have observed in the previous slide. So facts holds in situations rather than eternally. So every fact is represented in terms of a situation. For example, holding gold, comma now, rather than just holding gold, because the holding gold does not reflect that you are holding gold now, or you have holding gold previously, or you will hold it for the next time. So because it is better to represent the situation, so the situation is better represented by holding gold comma now. And for that purpose there is a way to describe these things, and normally we describe this in situation calculus, which represent all the situations as it is there in the given problem. So adds a situation argument to each non-eternal predicate. For example, we have seen that how the now is introduced in the holding one. So situation are connected by the result function as well. So result A comma S is the situation that results from doing A in the S. So let's assume that you have taken action, that your agent moves from 1 1 to 1 2. It's an action. So when you take that action, the new situation will come up. Or you are at 1 2 and you have chosen to fire an arrow, so it's an action. So you, if you take that action, your you will come up with a new state. So that is always represented as the result. And you can see here the actions as well. The effect axiom describe changes due to action. For example, for all x at gold x, let's assume that for all as at gold as कब होंगे, that implies that holding gold comma result grab comma s. So let's suppose the holding will be true if you are at gold and you have grabbed the gold, so it means you are at gold. For example, have arrow for all x have arrows implies have arrow result grab comma x, because if you have an arrow you have to grab it. So if you have grabbed it, it means you have an arrow. So what you've done is that you have described the action in terms of the given situation. So that is important when you talk about such actions. Similarly, you can represent these statements in a frame as well. From each axiom is about a predicate. So for every axiom, you have to come up with a predicate. And when it will be true, P true afterwards, then you use the double implication, an action made P true. So if that action makes P the true, then you use the by implication, or P true already and no action made P false, and P already true tha, there is no action that made the P false. So if the P will remain the true, so either the P will remain the true or your action will make the P to true. For example, in terms of holding the gold, for all A comma S, holding gold comma result A comma S, by conditional A is equal to grab and add gold S. What is your action? Action is grab. And of course, why you have taken that action? Because you are at gold at given point in time or a given state. Or you can say that holding gold X, so you have holded the gold X and A is not equal to release. You have not dropped it. You have not, it makes sure that you have not released it. So when you have not released it, you actually hold it. So that is the way in which we can represent those situations. And by doing so, we can make plans as well. Let's suppose you can see in the given slide that you have a query that asks the KB. What is the question? What is the query to the knowledge base? That there exists X, S, uh, holding gold comma S. That is, in what situation will I be holding the gold? That is the representation in the form of FOL query. The answer is that yes, S given, the result is that the grab result forward comma S not. Go forward and then grab the gold. So that is something which is represented to complete that particular statement. This assumes that the agent is interested in plans starting at S naught and that S naught is the only situation described in the KB. So S naught is given, and for by using that S naught you can make that given statement as you did in the case of go forward and then grab the gold. So that is the way in which these statements can be represented. Represent plan as action sequence. Yes, you can also represent your plan with an action sequence. Let's suppose in the Wumpus problem, you can define a sequence that you have to take the first action like this, then the second action is then, third action is this. If you define all those actions in a sequence, and obviously that always be in the sequence, so then it will be like A1, comma A2, comma dot dot dot, comma AN. So that represent the whole actions in the form of a set. So you are looking to plan a result. P comma S is the result of executing P in S. So whatever you have executed in P in the given state, based on the given action, so you can plan all the results and you can see what will happen. Then the query will be the ask KB that there exists P, what holding gold, comma plan the result P, comma S naught has the situation that P forward and grab. So if you are going to plan to hold the gold, so you have defined the state as naught and you have the solution that go forward and grab it. So that is already being defined in the action sequence on the top. So the definition of planned results in term of the result will give you the following statement that for all s, plan the result, whatever the actions you have, comma s will give you the s. For all a, comma p, comma s, plan the result, action a for the given plan and of course the given state that will give you the planned result of p, that is the outcome of the action a and the state in which you reached out. So planning systems are special purpose reasoners designed to do this type of inference more efficiently than a general purpose reasoner. So one is called general purpose reasoning and the other one is called a specialized. So planning systems are normally used for a specialized sort of reasoning. Now, the summary is that the first order logic is a different from propositional logic. In the first order logic, we have more expressions. We can define the objects, we can define the functions, and we can define the predicates, and we can define the quantifiers, equality, and constants and everything. We have more expressive power than the propositional form of logic. Then we have seen the Wumpus world problem to be represented in the form of FOL in this chapter. And in the last, we have talked about the situation calculus, that is about FOL. If you have any further queries, you may contact me during office hours or through email. Thank you.